Hello everyone and welcome back again. Ever wonder how your computer alters all the apps you have open at once? How does it decide which program gets to run and when? The magic behind this is called CPU scheduling. Today we are diving into the most common short-term scheduling algorithms that the CPU scheduler uses to keep everything running smoothly. Ready to peek under the hood of your operating system? Let's get started. First up, we have first come, first served, or FCFS. It is exactly what it sounds like. The first process to arrive is the first one to get the CPU. Imagine a queue at a coffee shop. The first person in line gets their coffee first. It's super simple to implement, which is its biggest plus. However, it has some major drawbacks. One is called the convoy effect. Picture a long, slow truck at the front of a single-lane road, holding up a line of fast sports cars behind it. In CPU terms, a long process can make many shorter processes wait, which kills efficiency and CPU utilization. This can also lead to starvation, where a process has to wait an incredibly long time just to get its turn. So how can we improve on that? Let's talk about shortest job first, or SJF. This algorithm is a bit smarter. Instead of just looking at who arrived first, it looks at the burst time, which is the amount of time a process needs to run. The process with the shortest burst time gets to go first. This is fantastic for minimizing the average waiting time for all processes. It is like letting the person with just one item go ahead of you in the grocery line. It makes the whole system faster. The catch: it's hard to know the exact burst time of a process in advance. Plus, longer processes might get pushed back continuously and starve for CPU time, which is a big problem. To tackle the issues with SJF, we have its dynamic cousin, shortest remaining time first, or SRTF. This is a preemptive version of SJF. Here is the difference. The scheduler doesn't just check the total burst time at the beginning. It continuously checks which running process has the least amount of time left to complete. If a new, shorter process arrives, the scheduler can pause the current one and switch to the new, quicker task. This makes the system very responsive and efficient. It's like a super efficient multitasker that's always working on the quickest thing first, which greatly improves overall throughput. Next, we have priority scheduling. In this system, each process is assigned a priority level. The CPU is always given to the process with the highest priority. This is great because it allows us to prioritize important system tasks over less critical user applications. For example, your antivirus scan might be given a higher priority than your music player. The main downside is, you guessed it, starvation. Low priority processes might never get to run if there's a constant stream of high priority tasks. To solve this, some systems use a technique called aging, where a process's priority gradually increases the longer it waits. Finally, let's look at one of the most popular and balanced algorithms: round robin. Think of it as a fair timeshare for the CPU. Each process gets a small, fixed amount of time on the CPU, called a time slice or quantum. It runs for that duration, and if it's not finished, it goes to the back of the line and waits for its next turn. This ensures that every process gets a chance to run, completely eliminating starvation. It feels very responsive to the user because even long processes make progress in small bursts. The main challenge is choosing the right time slice. Duration too short, and you waste time switching between processes. Too long, and it starts behaving like the less efficient FCFS. And there you have it. From the simple queue of FCFS to the fair play approach of round robin, these algorithms are the unsung heroes that make modern computing possible. Each has its strengths and weaknesses, and often real-world operating systems use a hybrid approach to get the best of all worlds. I hope this helped you understand a bit more about what is happening inside your computer. Thanks for watching, and I'll see you in the next one.